In this screencast, I'm going to talk about a few different concepts related to force. We'll talk about what forces are, we'll talk about Newton's second law, we'll talk about Newton's first law, and we'll do a brief introduction to the gravitational force law. So first, what is a force? Here's what a force is. It's a push or a pull by one object on another object. So there are always two objects involved, and if you are going to point to something and say, oh yes, that's a force, then you should be ready to answer the question, what object is exerting the force? So for example, here's a picture of an airplane, and it's above the ground, and we know that there's a gravitational force on the plane. What object exerts the force? The Earth. What object receives or experiences the force? Well, in this case, the airplane. What type of force is it? I guess I said it's the gravitational force that this plane is experiencing that I've chosen this picture to represent. Each force has a type. We'll learn about the different types of forces like friction and tension and something we'll call a normal force and the electrical force and the magnetic force. Each force has a type. Each force has a direction. For example, the direction of the force that the Earth exerts on that plane is down. And how much each force has a magnitude as well as a direction, and the magnitude of force is measured in newtons. We found in the lab that when we varied the amount of force applied to a cart, the acceleration that the cart has is proportional to the amount of force exerted on it. So this little alpha means is proportional to, the acceleration is proportional to the force in the experiment that we did. In the language of math, that means that the acceleration is some constant times the amount of force. And I'd like you to think, if you would, maybe even pause the video for a little bit, about what the physical significance of this constant is. You might even think, if there were a very big value of that c there, such that you had a great big acceleration from just a little force, what would that mean about the setup you had? Or if there was a very, very tiny value of that constant c there, such that you got only a very little acceleration from a big force, what would that mean about the setup that you had? And I'll suggest that that constant there is sort of like the sensitivity of an object. So if the cart is very, very sensitive, then it'll have a very big acceleration from just a small amount of force exerted on it. We also found, and this is actually related to maybe the sensitivity concept, that as we increased the mass of the cart, we decreased the acceleration of the cart in a way that was inversely proportional. The acceleration is inversely proportional to the mass. It's proportional to 1 over the mass. And so if you combine these concepts and maybe include the concept of sensitivity, we might say, oh, the acceleration of the cart is the force divided by the mass. And this is a true result for the particular lab that we did, but you'll notice that I haven't circled it. It's not a main physics law for you to learn. That is coming up. But a brief deviation before we do that. If you take a look, I guess we said that the unit of force is newtons. We measure force in newtons. But this equation up here shows that, I guess if you look at the units of the left side, acceleration in meters per second squared has to be equal to whatever the unit of force is, newtons, divided by kilograms. In other words, a newton is a kilogram meter per second squared. So the unit of force is actually defined in terms of the base SI units, the unit for mass, kilograms, the unit for distance, meters, and the unit for time, seconds. A 1 Newton force is a force that would yield a 1 meter per second squared acceleration in an object whose mass is 1 kilogram. However, if I ask you, what's the acceleration of this object? Well, it's mathematically true that you could respond in newtons per kilogram, report accelerations in meters per second squared. So now here I'd like you to imagine a cart that has maybe one fan on that tends to drive it to the left and one fan on that tends to drive it to the right. Would you say that the acceleration is 2 times F divided by the mass of the cart, or what's the deal here? I think you have a sense that the acceleration is 0, that there's actually some cancellation. This rightward force would cancel that leftward force, yielding 0 acceleration. In other words, the acceleration of an object comes from a combination of forces acting on its mass. This is Newton's second law and is one of the key physics laws that we will cover this year. The acceleration comes from a combination of forces acting on a mass. So we're going to ask a number of Newton's second law problems, and I would like to show you how I recommend writing them. I promise that very shortly we will have problems that challenge you with Newton's second law, so that I can show you the writing techniques, or so that I can show you some thoughts that will be useful and some ways to hold those thoughts. Here I'm asking a very easy problem. Let's say that there's a 2 kilogram block on a frictionless surface, and I apply one force of 4 newtons directed to the right, and one force of 10 newtons directed to the left. I want to ask, what is the acceleration of the block? So sometimes it's a good idea to draw a little cartoon to yourself, and the rules of a cartoon is that you can draw whatever you want. But after that, you should make a qualitative representation. And if you remember, in a qualitative representation, we distill the problem down to just the elements that are important and intentionally take out all of the details, especially the numbers, that aren't really important to understanding what's physically going on. So let me show you the qualitative representation that is relevant to force problems. We'll end up making a lot of them, and it's called a free body diagram. It shows the forces on one object at one instant. We make a dot and label it with the mass of the object. So this block I'm approximating as a particle, as we did when we were in our kinematics unit, and saying, oh yeah, that dot right there, that's the block. We draw arrows from the object, not into the object, to indicate the forces on it. If you know what the type of force is, if you know that, for example, it's a normal force or a tension force, you should label that in the labels of these force arrows. However, in this problem, I don't think I specified what type of forces are acting, so I just called it F1 and F2. Use relative lengths of arrows to show if arrows are to show if forces are greater or lesser in magnitude. And this is important. Don't include anything else. Do not put a number associated with what that force is. We're in the business of just asking the question, what forces are acting? And that's it. We'll deal with values and everything else later. As with the way we talked about doing this in kinematics, the next step is to transcribe the values of the problem. The mass of the block is 2 kilograms, and there are the values of the two forces, and indicate the thing that you're looking for, the desired variable. So then, I encourage you to make a Newton's second law statement about the object. And a Newton's second law statement is basically a way of rewriting the acceleration as the combination of forces divided by the mass. Specifically, you write out how the forces combine. If you look at this free body diagram, which I've just copied down here so you can see it at this point in the slide again, what direction is this object accelerating? To the left. You know that. So we've already solved for the direction of the acceleration. Let's just solve for the magnitude of the acceleration. The leftward acceleration comes from the leftward force diminished by the rightward force. The acceleration is equal to F2 minus F1, where I consider both forces positive. There are other ways that you could write the combination of forces, and I actually have a worksheet about which of those ways are basically okay, and also some ways that a person could make some mistakes in doing that. That is part of the assignment following this lecture. But for right now, I hope that you'll agree with me that the acceleration is to the left, and here's one way to get the amount of the acceleration. Substitute with units. 10 newtons minus 4 newtons divided by 2 kilograms is 3 meters per second squared. That is the acceleration that the block will have to the left. I'd like to talk about F equals ma, which you've probably heard because it's out there in culture. Physics teachers don't really say F equals ma for reasons that I'd like to talk about. First of all, what's the acceleration of this block here that has a rightward force on it and a leftward force? Or I guess maybe I could ask, is this force equal to, is the force F1 equal to the mass m times the acceleration of the block? Or is it this force that's equal to ma? Or what's up? An object only has one acceleration. You can't be like, oh yeah, the acceleration associated with that force is like F over m, and then there's a separate acceleration from that force, and then those accelerations combine. An object only has one acceleration because it only has one position and 1 second derivative of that position. So basically what I'm trying to say is that F equals ma would only be true if exactly one force is acting. We actually had a situation like that with the cart in our lab. But in most situations, objects have multiple forces acting on them. If anything, the combination of forces, that's the Greek letter sigma, would be equal to the mass of an object times acceleration. This is at least a true statement, but I'd like to see if we can adopt Newton's second law framed with the acceleration being equal to the combination of forces divided by the mass, rather than the combination of forces being equal to ma. And so why would I do that? Well, check this out. Remember our constant velocity equation? Delta x equals v delta t. It would also have been true to say delta t equals delta x over v. These are mathematically equivalent, but we memorized this one. This is the one that I put dashed hot pink around. And I have a reason for that. It's because this sort of highlights cause and effect, with an effect on the left-hand side and a cause on the right-hand side. When you have a velocity that persists for some amount of time, that causes a displacement to occur. That sense of causality is really just lost in this other way of mathematically writing it. It's not that a change in time is caused by a displacement being divided by a factor of a velocity. So there's something kind of nice about this that relates to causality. In other words, you have a happy face for the causal equation and a sad pug face for the equation that's merely true. What's the formula for the area of a circle? Or what's the relationship between the radius and an area of the circle? I think that you memorized this equation in your math class, not this one. And I think that was a really good choice, because it's kind of like a radius having a certain value causes an area to be what it is, rather than some value of area causing the radius of a circle be what it is. Now really, there isn't strict causality there. Both the radius and the area exist at the same time. But I think we can sort of feel like there's some causality. Based on what the radius is, here's what the area is. And I think that's good. I think that's desirable. I think it's okay. And it's desirable for us here, too. A cause, a combination of forces acting on a mass, produces an effect, an acceleration of the mass. Here, I've got no sense of causality. So just like when you write down the formula for an area of a circle in math class, and you write a equals pi r squared, even when you're solving for r, let's start our communications about Newton's second law by saying that the acceleration is equal to the combination of forces divided by the mass. Here, I'd like to talk about what happens when no forces act on an object, and this is a little cartoon of a moose that is floating out through space. And I don't know if you can make out there's a cupcake in front of it. So if there's no force at all acting on an object, then its acceleration is zero. Zero force divided by the mass of the object is zero acceleration. And if an object has zero acceleration, its velocity is going to be constant. When no forces act on an object, its velocity is constant. What about when forces act on an object, but those forces balance or cancel out. For example, if I have this block here and there's a 10 Newton force to the left of it, to the left on it, and a 10 Newton force to the right exerted on it. Well, I guess this rightward force cancels with that leftward force, and again, there's no acceleration, and so the velocity is again constant. When you combine these observations, you get Newton's first law, which says that an object will stay at a constant velocity unless a net force acts on it. Here, there were forces acting on this block, but there was no net force. Rest, v equals 0, is an example of constant velocity, but you can have this mousse floating through space with this cupcake at constant velocity. I guess in this picture, the mousse is damned never to actually catch up to the cupcake, and so it will just be sort of taunted by the cupcake floating in front of it for all eternity by Newton's first law. Newton's first law relates to a physics concept called inertia, which is an object's tendency to stay at a constant velocity, including rest. If you imagine a great big bowling ball rolling down a bowling lane, it tends to keep rolling. It has a large inertia sort of related to its large mass. If you were to roll a ping pong ball down the same bowling lane, there isn't quite as much inertia in the ping pong ball, so there's less of a tendency for it to continue progressing. Of course, in the absence of all forces, both the bowling ball and the ping pong ball would continue at constant velocity. You can watch that video if you want. It's of Paul Hewitt explaining about inertia. But Newton's first law, this law, that objects stay at constant velocity in the absence of a net force, is the law of inertia. What's going on here is this hand is getting ready to rip that piece of paper towel out from that coin, and because it happens so rapidly, the coin's tendency to stay at constant velocity, its tendency to stay at rest, will mean that it doesn't actually move as a result of the paper towel being ripped out. It will fall into the cup. That's a demo that physics teachers love to do. Newton's first law, the law of inertia. So here's a problem that I'd like to talk to you about, and that we'll do a couple of examples like this. If we have our friend the block with a force to the right and a force to the left, and the mass and the magnitude of each force is known, could you tell me how much time it would take for this block to experience a certain displacement if it's moving from rest? I think you could, and I'm not going to solve the whole thing out, but briefly, you could use Newton's second law to find the acceleration of this block, and then you could use your kinematics, your constant acceleration skills, to find how much time is taken to move a certain displacement from rest given that acceleration. One last topic, and that is the force law for gravitational force. And when we meet next, I'll do a little demo for you in Logger Pro to verify this. But actually, I think you actually know enough physics to know what I'm about to say anyway. On Earth, an object that has a mass m experiences a gravitational force down towards the center of the Earth, and that gravitational force has a magnitude mg, where m is the object's mass, and g is our old friend 9.8 meters per second squared, 10 meters per second squared. As we talked about during kinematics, there are different values for g, the local gravitational field, or the local acceleration due to gravity, at different places in the universe. And we will actually get good at calculating the value of g around gravitating bodies. But for now, on Earth, g has the value of about 10 meters per second squared, and therefore the gravitational force on a mass m is about m times 10 meters per second squared. So here, let's do an example. Let's say I drop a mass m from a window. What is its acceleration? Well, there's a free body diagram. Only gravity acts on it. It acts in the downward direction. There's the mass labeled m. The acceleration is the combination of forces divided by the mass. And there's only one force, the gravitational force, mg. And look, the mass cancels. So no matter what the mass of an object is, its acceleration has a magnitude of g. No matter the mass, you have the same acceleration. it's equal to g down. This is the dramatic result that Galileo is said to have shown by dropping objects of different mass off of the Leaning Tower of Pisa and showing that they had the same downward acceleration. Here's a vocabulary word, weight. The weight of an object is its gravitational force, the gravitational force acting on it. The weight of an object is the gravitational force acting on it. Weight is not the same as mass. An object of mass, m, has a weight, mg. So if I go to the moon, does my mass change? Does my weight change? Well, my mass is related to how much mass is in all of my atoms and molecules, my protons and neutrons and electrons. That doesn't change when I go to the moon. However, the value of g does change when I go to the moon. So my weight changes, but not my mass. The units of weight are newtons. And that's all.